let's need to start. So since I'll probably go for another 15 to 20 minutes extra today. So in the past 3 lectures, we've been covering basic integrability in the classical mechanics. So in today's, I guess, 2.5 hours lectures, I'm hopefully trying to introduce you to the idea of integrability in the quantum mechanical system. And rather than, it's basically impossible to actually cover all the kind of even well-known integrable model, quantum integrable model in the 2.5 hours. But I will focus on probably one of the best known example, and probably the one with the most applications in both condensed matter physics, mathematical physics, and the high-energy physics. And this model is something called XSX, Heisenberg spin chain. And the aim of today's lecture is trying to demonstrate how you can use a kind of standard technique in the integrable system literature known as algebraic Besser ansatz to not only find the eigenvalues or basically various expectation values for the kind of physical conserved charges associated with the XSX spin chain, but also how we can construct the eigenfunctions for the spin chain. So we'll try to do this step by step. Of course, some of you may encounter this class of model like yesterday. I think Yong Quan was mentioning it. And of course, the problem of finding the eigenfunction is really just a diagonalization problem. But it turns out that for most of the physical situations we are dealing with, well, it's basically Heisenberg spin chain modeling a line of electron. But usually, for example, in a real condensed matter system, you'll be dealing with a large number of electrons, and the actual diagonalization becomes a very difficult problem. Like if you try to, because you have to solve polynomial equation at very high degrees, and your computer simply just breaks down. Okay, so let's try to do step by step. See how far we can go. So unfortunately, some of the steps, like I'll be talking about in today's lecture, I guess I won't have time to actually flesh out all of them on a blackboard. But hopefully, in the notes, probably it's on the web now, you can actually follow it. So to prepare today's lecture, so I guess I give a title, so intro to algebraic Besser ansatz and spin chain. And in preparing today's lecture, I have borrowed quite heavily a set of classic lecture notes prepared by a very, very famous Russian physicist called Fadeev. It's in the Fadeev Top of Ghosts. And so those notes you can actually find it freely on the web, and it goes by the archive number. And also another set slightly earlier, with similar content. Okay, so of course, the notes covered by Fadeev cover far more material than I will be talking about today. But hopefully, after today's lecture, you'll be able to pick up. If you are interested in learning more about Besser ansatz, you'll be able to pick up Fadeev lecture notes. Okay, so before I go straight into the spin chain, let me just give some brief comments about, I guess, general structure of a lattice model, and also, I guess, set the notation for today's lecture. So generally, when we consider lattice model, at least in this context, we'll be considering something like a discrete circle. Okay, so there are different lattice sides on a circle. And there could be some degree of freedom, like usually you have electrons or some other molecules sitting on it. And so usually we'll label those different lattice sites by some index small n and by periodicity. So altogether, we'll assume they are totally capital N of the discrete points on a circle. So we naturally make an identification of n plus n to n. And to ensure the periodicity on various kind of observables. So for example, for each site, we can associate with some observables, which are usually denoted as x and alpha. And this index here is simply labeling which site you're on. And we are going to identify the indices will be shifted by capital N to ensure periodicity. So I hope it's obvious. And we take a separation between the different, usually take a separation between different lattice sites to be something like a delta. Okay? So what we usually call a lattice coordinate are usually just given by n times delta. So n can run from I guess 1 capital N. Okay? That's also obvious. And when we say in a continuous limit, or sometimes people denote as thermodynamical limit. That simply means that we take delta, or basically lattice spacing between different sites, get smaller and smaller, tending to 0, and also at the same time treating the number of the different sites goes to infinity. So basically now you have a continuous distribution of basically, for example, electrons or other molecules along those lines. So this really becomes just something like a continuous coordinate, which usually would denote as x. So hopefully all these are intuitive and obvious. And finally, that in a lot of those manipulations, we'll be dealing with Canonical delta. And in a continuous limit, that we have to basically size it by the lattice spacing. In the continuous limit, the Canonical delta usually just simply go over to the Dirac delta function. Okay. All right. So usually, what we are really going to study is on each of. So how many of you did quantum mechanics? You know Hilbert space, do you? Okay, good. So basically, what we are studying in this lecture is basically trying to study the algebra. So based on each lattice size, there will be a sorry. Which one? 这个是大写。它是变成是说你变成有 infinite number， 你的 number of spins gets larger and larger. Sorry, 你的 number of different size 变成。小写只是一个 sorry 小写 yeah okay it's a bad notation it could be if you don't like it go L. 它只是告诉你说1、2、3、4。也就是 indirectly bring like once again， 告诉你现在在哪个lattice size。Okay. All right. So in this context, we basically will be studying how. So as I mentioned just now, that on each side there will be a dynamical, there could be some observables. And if we're studying a quantum mechanical systems, those observables are usually become some kind of operators, right? Like this momentum operator, like could be angular momentum operator, position operator, and so on. So what we are really interested is trying to study the algebra among those different quantum mechanical operators. So let me just write some words. So yeah, so usually when we are studying, so eventually we'll be studying something like this. Okay, that's a better way to say it. So we'll be studying different kind of commutator between different observables, and you can view them as some kind of matrix. In fact, I think for all the operators we'll be studying in this lecture, it will be just x alpha m can be represented as some kind of matrix, and they will be acting on the Hilbert space. Well, basically, you can view it just as a vector space sitting at each lattice site. Okay, so we'll be studying what those guys actually are, and from those we're trying to solve the eigenvalue. So of different operators. So, and the particular case we'll be interested in this lecture is to do it's basically something called ultra local case, which simply tells you that is equal to 0 if m is not equal to n. So basically commute with each other. Or in other words, that if we are not looking at the operators defined or acting on the same lattice site, and they will commute with each other. So basically, that restrict kind of interaction range. But generally, you don't have to have that. I mean, in fact, this is a kind of good first approximation that when we usually do in the condensed matter physics, that we only restricted kind of short range interaction. But in general, you can have this guy to be 0, but you can extend it. So generally, we count this 0 only when kind of n minus n is greater than some numbers. It depends on how many, for a given lattice site here, how many kind of neighboring sites you would talk to. Okay? And if they have interaction, then generally you expect the operator associated with each of those sites do not commute with each other. Okay? Even though those are just some simple mathematical definition, but hopefully that you can appreciate that the kind of physical meaning in imposing those various kinds of constraints. Okay, so we'll be focusing mostly on the ultra-local case. Therefore, so for example, on each side, let me just give you a couple of examples, and you get an idea what I'm talking about. So for the ultra-local case, we can write down the commutation relation. Between, for the canonical variables, or basically the position variable phi alpha n and phi alpha n, and alpha goes 1 to L, take some finite values. for those of you, okay, we'll get to that. I will get to that. So the commutational relation between them is simply given by zero, on the other hand. H bar, so that's the Planck constant, times delta Mn, delta alpha beta, and there could be some unit matrices. So, so this is, some of you might recall, this is actually this is basically a Heisenberg uncertainty principle. Well, okay, I mean Heisenberg commutator. Uncertainty principle between position and momentum. Okay, in quantum mechanics. But now we generalize this to a different lattice size. So it will soon become clear what this all means. I'm just writing down. So a particular class of observables who will be interested are the usual kind of spin associated with each lattice size. So for example, if you have an electron, so you can spin up, spin down, or other representation given whatever symmetry group you have at each lattice side. You'll be interested in their value, in the value of their spins. So spin observables from each lattice side, this, and those operator as alpha m, beta n, satisfy the following commutational relation. This is actually, for those of you who know that for fixed m, obviously when m and m are equal, then this actually gives the copies of so-called SL2 algebra. So the picture you should have in mind is really that on each lattice side, there's actually a SL2 algebra acting on it. And each of those states actually form, each of those lattice side or electron actually form a representation on the this SL2 algebra. Okay. So, and precisely which representation you have, it depends on the quantum number carried by those lattice side, or basically the spins of them. So each. So are you familiar with this language, like electron spin labeled by SL2, this kind of algebra for at least fixed M and M? Have you seen Pauli matrices? Representation of SU2. For those of you who don't apply math 4, they should know what's going on. All right. for each lattice site, we've seen this before. The SU2 algebra in 数四. We have a finite dimensional representation of SL2 and labeled by spin S. Okay, so this representation of SL2, or sometime we'll be calling in this lecture as a kind of Hilbert space sitting precisely at the site n, and we'll denote it as Hn. It's of a dimension C2S plus 1. So, for example, for I guess the spin half case, okay, so the dimension of the Hilbert space will be basically 2 copies of a complex plane. Well, basically take a value. It depends on 2 independent complex numbers. So actually, so for the S equal half case, we can explicitly realize those different S operators using the Pauli matrices. For each n. Okay. So those are 2 by 2 matrices. One particular representation which we'll be using. In this lecture. So if you want, for each of those Hilbert space, we are looking basically at some column vector with 2 entries, and those entries, each of them will be a complex number. So that's why I'm identifying the Hilbert space as a dimension C2. Okay? So, but what's really nice about it is that, so I'm presenting those 2 different algebra. One is for the momentum position, and the other one is for the spin. Is that we can actually express those commutation relation for the SL2 algebra in terms of a Heisenberg algebra. And what I meant by this is that so for a set of a canonical variables, alpha and pi, so on, and we can define how many of you seen the creation and annihilation operator method to solve simple harmonic oscillators? How many of you not seen that? So everyone is remain neutral today. can define the following operators just by using the linear combination of them. So, so occasionally, actually, I will set h bar equal to 1. All right. So, unless otherwise stated. So, when we define those, then psi and psi star obey the following commutation relation. So we can actually represent the those generator for the SL2 in terms of psi and psi star as following. So S labeling the spins of the particular representation. So you can verify those. So the reason for that was, if you recall, that yesterday when we were talking about phase space, today we're talking about phase space, we are basically expressing everything in terms of the canonical variables for the position and momentum coordinates. And now we are basically promoting those guys to a quantum mechanical operators. And on the other hand, there could be another set of physical observable, which we are usually really interested. We don't label the each lattice sign in terms of momentum position, but usually we are interested in their spins. But however, this relation tells you that you can actually rewrite those spin degree of freedom in terms of the original canonical variables, and therefore we can actually cast various kind of dynamical variable by this kind of change of a spin degree of freedom into those momentum position into a quantum mechanical version of the phase space. So this will be useful later. I mean, I'm trying to write this out. It's because later when we are constructing the quantum mechanical commuting conserved charges, which will ensure the quantum integrability, and when we count the number of them, it's important to realize that we still just need, for example, for a n lattice side, we still just need an n, even though we are interested in the spin degree of freedom, that we only really need an n commuting conserved charges only. Okay. And the final word about you should be curious about what what are those indices on the lattice that actually mean. I mean, well, how do you actually calculate if you want to use those definitions? So what this really means is that it's very simple. Looking at a Hilbert space,